Surface chemistry deals with the phenomena that occur at the surface or interfaces. The interface or a surface is represented by separating the bulk phases by a halcyon or a slash. For example, the interface between a solid and a gas may be represented by solid gas or a solid oblique gas. Due to complete miscibility, there is no interface between the gases. The bulk phases that we come across in surface chemistry may be pure compounds or solutions. The interference is normally a few molecules thick, but its area depends on the size of the particles of bulk phases. Many important phenomena noticeable amongst these being corrosion, electrode processes, heterogeneous catalysis, dissolution, and crystallization occur at interfaces. The subject of surface chemistry finds many applications in industry, analytical work, and daily life situations. To accomplish surface studies meticulously, it becomes imperative to have a really clean surface. Under very high vacuum of the order of 10 to the power minus 8 to 10 to the power minus 9 Pascal, it is now possible to obtain ultra clean surface of the metals, solid materials, which such clean surfaces need to be stored in vacuum, otherwise this will be covered by molecules of the major components of air, namely dioxygen and dinitrogen. Catalysis. Potassium chlorate, when heated strongly, decomposes slowly, giving dioxygen. The decomposition occurs in the temperature range of 653 to 873 Kelvin. However, when a little of manganese dioxide is added, the decomposition takes place at a considerably lower temperature range. Decomposition takes place at a considerably lower temperature range, that is 473 to 633 Kelvin, and also at a much accelerated rate. The added manganese dioxide remains unchanged with respect to its mass and decomposition. In a similar manner, the rates of a number of chemical reactions can be altered by the mere presence of a foreign substance. The systematic study of the effect of various foreign substances on the rates of chemical reactions was first made by Berzelius in 1835. He suggested the term catalyst for such substances. Substances which accelerate the rate of chemical reaction and themselves remain chemically and quantitatively unchanged after the reaction are known as catalysts, and the phenomenon is known as catalysis. Promoters and poisons. Promoters are substances that enhance the activity of catalyst, while poisons decrease the activity of catalyst. For example, in Haber's process for manufacture of ammonia, molybdenum acts as a promoter for iron, which is used as a catalyst. Homogeneous and heterogeneous catalysts. Catalysis can be broadly divided into two parts. First, homogeneous catalysis, when the reactants, products, and the catalyst are in the same phase, that is, liquid or a gas, the process is said to be homogeneous catalysis. The following are some of the examples of homogeneous catalysis. Oxidation. First, oxidation of a sulfur dioxide into sulfur trioxide with dioxygen in the presence of oxides of a nitrogen as the catalyst in the leader chamber process. The reactants sulfur dioxide and oxygen and the catalyst nitric oxide are all in the same phase. Second, hydrolysis of methyl acetate is catalyzed by H plus ions furnished by hydrochloric acid. Both the reactants and the catalyst are in the same phase. Third, hydrolysis of a sugar is catalyzed by H plus ions furnished by sulfuric acid. Both the reactants and the catalyst are in the same phase. Second groups of catalysis is heterogeneous catalysis. The catalytic process is in which the reactants and the catalyst are in different phases is known as heterogeneous catalysis. Some of the examples of heterogeneous catalysis are given below. First, oxidation of a sulfur dioxide into sulfur trioxide in the presence of platinum. The reactant is in a gaseous state while the catalyst is in the solid state. Second, combination between dinitrogen and dihydrogen to form ammonia in the presence of finely divided iron in Haber's process. The reactants are in a gaseous state while the catalyst is in the solid state. Third, oxidation of ammonia into nitric oxide in the presence of platinum gauze in Ostwald's process. The reactants are in a gaseous state while catalyst is in the solid state. Fourth, hydrogenation of vegetable oils in the presence of finely divided nickel as a catalyst. One of the reactants is in liquid state and other in the gaseous state while the catalyst is in the solid state. Adsorption theory of heterogeneous catalysis. The theory explained the mechanism of heterogeneous catalysis. The old theory, known as adsorption theory of catalysis, was that the reactants in gaseous state or in solutions are adsorbed on the surface of the solid catalysis. On the surface of the solid catalyst. The increase in concentration of the reactants on the surface increases rate of reaction. Adsorption being an exothermic process, the heat of adsorption is utilized in enhancing the rate of reaction. The catalytic action can be explained in terms of the intermediate compound formation. The modern adsorption theory is the combination of intermediate compound formation theory and the old adsorption theory. The catalytic activity is localized on the surface of a catalyst. The mechanism involves 5 steps. First step, diffusion of reactants to the surface of the catalyst. Second, adsorption of reactant molecules on the surface of the catalyst. Third, occurrence of chemical reaction on the catalyst's surface through formation of an intermediate. Fourth, desorption of reaction products from the catalyst surface and thereby making the surface available again for more reaction to occur. Fifth, diffusion of reaction products away from the catalyst surface. The surface of the catalyst, unlike the inner part of the bulk, has free valencies which provide the seat for chemical forces of attraction. When a gas comes in contact with such a surface, its molecules are held up there due to loose chemical combination. If each other resulting in the formation of new molecules, thus formed molecules may evaporate, leaving the surface for the fresh reactant molecules. This theory explains why the catalyst remains unchanged in mass and chemical position at the end of the reaction and is effective even in small quantities. It, however, does not explain the action of catalytic promoters and catalytic poisons. Important features of solid catalysts. First, activity. The activity of the catalyst depends upon the strength of chemisorption to a large extent. The reactants must get adsorbed reasonably strongly on the catalyst to become active. However, they must not get adsorbed so strongly that they are immobilized and other reactants are left with no space on the catalyst surface for adsorption. It has been found that for a hydrogenation reaction, the catalytic activity increases from group 5 to group 11 metals, with maximum activity being shown by groups 7 to 9 elements of the periodic table. Second important features of a solid catalyst is selectivity. The selectivity of a catalyst is its ability to direct a reaction to yield a particular product selectively when under the same reaction conditions many products are possible. Selectivity of different catalysts for some reactants is different. For example, starting with H2 and CO and using different catalysts, we get different products. Thus, it can be inferred that the action of a catalyst is highly selective in nature. As a result, a substance which acts as a catalyst in one reaction may fail to catalyze another reaction. Colloids. We know that sand in water, when stirred, gives a suspension which slowly settles down with time. Between the two extremes of suspensions and solutions, we come across a large group of systems called colloidal dispersions or simple colloids. A colloid is a homogeneous system in which one substance is dispersed phase as very fine particles in another substance called dispersion medium. The essential difference between a solution and a colloid is that of particle size. While in a solution, the constituent particles are ions or small molecules, in a colloid, the dispersed phase may consist of particles of a single macromolecule such as a protein or a synthetic polymer or an aggregate of many atoms, ions, or molecules. Colloidal particles are larger than simple molecules but small enough to remain suspended. Their range of diameters is between 1 and 1000 nanometer, means 10 to the power minus 9 to 10 to the power minus 6 meter. Colloidal particles have an enormous surface area per unit mass as a result of their small size. Consider a cube with 1 centimeter side. It has a total surface area of 6 centimeter square. If it were divided equally into 10 to the power 12 cubes, the cubes would be the size of large colloidal particles and have a total surface area 60,000 centimeter square or 6 meter square. This enormous surface area leads to some special properties of colloids to be discussed later in this unit. Classification of colloids. Colloids are classified on the basis of the following criteria. First, physical state of a dispersed phase and dispersion medium. Second, nature of interaction between dispersed phase and dispersion medium. Third, type of particle of a dispersed phase. Point. Classification based on physical state of a dispersed phase and dispersion medium. Depending upon whether the dispersed phase and the dispersion medium are solids, liquids, and gaseous, 8 types of colloidal systems are possible. A gas mixed with another gas forms a homogeneous mixture and hence is not a colloidal system. Many familiar commercial products and natural objects are colloids. For example, whipped cream is a foam, which is a gas dispersed in a liquid. Firefighting foams used at emergency airplane landings are also colloidal systems. Most biological fluids are aqueous sols, means solids dispersed in water. Within a typical proteins and nucleic acids are colloidal sized particles dispersed in an aqueous solution of ions and small molecules. Out of various types of colloids given in the most common are sols, solid in liquid, gels, liquid in solids, and emulsions, liquid in liquids. However, in the present unit, we shall take up discussion of the sols and the emulsions only. Further, it may be mentioned that if the dispersion medium is water, the sol is called aquasol or hydrosol, and if the dispersion medium is alcohol, it is called alkosol, and so on. Colloids around us. Most of the substances we come across in our daily life are colloids. The meals we eat, the clothes we wear, the wooden furniture we use, the houses we live in, the newspaper we read are largely composed of colloids. Following are the interesting and noteworthy examples of colloids. Blue color of the sky. First, blue color of the sky. Dust particles along with water suspended in air scatter blue light which reaches our eye and the sky looks blue to us. Second, fog, mist and rain. Rain. When a large mass of air containing dust particles is cooled below its dew point, the moisture from the air condenses on the surfaces of these particles, forming fine droplets. These droplets, being colloidal in nature, continue to float in air in the form of mist and or fog. Clouds are aerosols, having small droplets of water suspended in air. On account of condensation in the upper atmosphere, the colloidal droplets of water grow bigger and bigger in size till they come down in the form of rain. Sometimes the rainfall occurs when two oppositely charged clouds meet. It is possible to cause artificial rain by throwing electrified sand or spraying a sol carrying charge opposite to the one on clouds from an aeroplane. Third, food articles, milk, butter, halwa, ice creams, fruit juices, etc. are all colloids in one form or the other. Fourth, blood. It is a colloidal solution of an albuminoid substance. The styptic action of alum and ferric chloride solution is due to coagulation of blood forming a clot which stops further bleeding. Fifth, soils. Fertile soils are colloidal in nature, in which humus acts as a protective colloid. On account of colloidal nature, soils absorb moisture and nourishing materials. Sixth, formation of delta. River water is a colloidal solution of a clay. Seawater contains a number of electrolytes. When river water meets the seawater, the electrolytes present in seawater coagulate the colloidal solution of clay, resulting in its deposition with the formation of a delta. Applications of colloids. Colloids are widely used in industry. Following are some examples. First, electrical precipitation of a smoke. Smoke is a colloidal solution of a solid particles such as carbon, arsenic compounds, dust, etc. in air. The smoke before it comes out from the chimney is laid through a chamber containing plates having a charge opposite to that carried by smoke particles. The particles, on coming in contact with these plates, lose their charge and get precipitated. The particles thus settle down on the floor of the chamber. Second, purification of drinking water. The water obtained from natural sources often contains suspended impurities. Alum is added to such water to coagulate the suspended impurities and make water fit for drinking purposes. Third, medicines. Most of the medicines are colloidal in nature. For example, argyrol is a silver sol used as an eye lotion. Colloidal antimony is used in curing kala azar. Of course, it is a disease. Colloidal gold is used for intramuscular injection. Milk of a magnesia and emulsion is used for stomach disorders. Colloidal medicines are more effective because they have a large surface area and are therefore easily assimilated. Fourth, tanning. Animal hides are colloidal in nature. When a hide which has positively charged particles is soaked in tannin, which contains negatively charged colloidal particles, mutual coagulation takes place. This results in the hardening of leather. This process is termed as tanning. Chromium salts are also used in place of tannin. Fifth, cleansing action of soaps and detergents. Sixth, photographic plates and films. Photographic plates or films are prepared by coating an emulsion of light sensitive silver bromide in gelatin over glass plates or celluloid films. Seventh, rubber industry. Latex is a colloidal solution of rubber particles which are negatively charged. Rubber is obtained by coagulation of latex. Eighth, industrial products, paints, inks, synthetic plastics, rubber, graphite, lubricants, cement, etc. are all colloidal solutions. Emulsions. These are liquid-liquid colloidal system. The dispersion of finely divided droplets in another liquid. If a mixture of two immiscible or partially miscible liquids is shaken, a coarse dispersion of one liquid in the other is obtained, which is called emulsion. Generally, one of the two liquids is water. These are two types of emulsions. First, oil dispersed in water, and second, water dispersed in oil. In the first system, water acts as a dispersion medium. Examples of this type of emulsion are milk and vanishing cream. In milk, liquid fat is dispersed in water. In the second system, oil acts as a dispersion medium. Common examples of this type are butter and cream. Emulsions of oil and water are unstable and sometimes they separate into two layers on standing. For stabilization of an emulsion, a third component called emulsifying agent is usually added. The emulsifying agent forms an interfacial film between suspended particles and the medium. The principal emulsifying agents for oil in water emulsions are protein, gums, natural and synthetic soaps, etc. And for water dispersed in oil, heavy metal salts of fatty acids, long chain alcohol, lamp black, etc. Emulsions can be diluted with an amount of the dispersion medium. On the other hand, the dispersed liquid, when mixed, forms a separate layer. The droplet in emulsions are often negatively charged and can be precipitated by electrolytes. They can also show Brownian movement and Tyndall effect. Emulsions can be broken into constituent liquids by heating, freezing, and centrifuging, etc. Adsorption is the phenomenon of attracting and retaining the molecules of a substance on the surface of a solid, resulting into a higher concentration on the surface than in the bulk. The substance adsorbed is known as adsorbate, and the substance on which adsorption takes place is called adsorbent. In physisorption, adsorbate is held to the adsorbent by weak van der Waals forces, and chemisorption, adsorbate is held to the adsorbent by strong chemical bond. Almost all solids adsorb gases. The extent of adsorption of a gas on a solid depends upon the nature of a gas, nature of solid, surface area of the solid, pressure of a gas, and net temperature of a gas. The relationship between the extent of adsorption and the pressure of the gas at constant temperature is known as adsorption isotherm. A catalyst is a substance which enhances the rate of a chemical reaction without itself getting used up in the reaction. The phenomenon using catalyst is known as catalysis. In homogeneous catalysis, the catalyst is in the same phase as are in the R reactants, and in heterogeneous catalysis, the catalyst is in a different phase from that of the reactants. Colloidal solutions are intermediate between true solutions and suspensions. The size of colloidal particles range from 1 to 1000 nanometer. A colloidal system consists of two phases, the dispersed phase and the dispersion medium. Colloidal systems are classified in a three-way depending upon first physical state of the dispersed phase and the dispersion medium, nature of the interaction between the dispersed phase and dispersion medium, and third, nature of particles of a dispersed phase. The colloidal systems show interesting optical, mechanical, and electric properties. The process of changing the colloidal particles in a sol into the insoluble precipitate by addition of some suitable electrolytes is known as coagulation emulsions are colloidal systems in which both dispersed phase and dispersion medium are liquids. This can be of first oil in water type and second water in oil type. The process of making emulsion is known as emulsification. To stabilize an emulsion, an emulsifying agent or emulsifier is added. Soaps and detergents are most frequently used as emulsifiers. Colloids find several applications in industry as well as in daily life also.